before we prove our next theorem, I just want to go back and reanalyze this theorem that Z is a PID. So what did we do? We started with a non-zero ideal. We found somehow a minimal element in it. A minimal, in this case, minimal positive element. And then we argued that that minimal positive element principally generated it. One of the directions was there was no work. The other direction used the division algorithm. We used the division algorithm to see that, that it actually was principally generated by that. So this seems to indicate that if we have some way of like picking a minimal element in a ring somehow, where minimal, I'm not going to define, and we have access to the division algorithm, then we could probably reproduce this proof. And so that's what we're going to do. So theorem, let F be a field, then the ring of polynomials over F is a PID. Proof, well, we already know that this is a domain. We knew that Z, we've been sort of using that Z as a domain in the previous proof, although I didn't write it out. So we know it's a domain because F is a field. In particular, F is a domain. So ring of polynomials over a domain is a domain. We just need to show that all the ideals are principal. The zero ideal is always principal. So zero ideal is principal. It's generated by 0. So let's take a non-zero ideal. And we need to show that it's principal. Okay, so if the previous argument, if the previous sort of guide is to be believed, we should somehow look for a smallest element, and then we should try to apply the division algorithm. So what should a smallest element be here? Well, the division algorithm is for polynomials is an algorithm about degree. So we should look for an element of least degree. So we're going to do exactly that. We're going to set S to be the collection of all degrees of F's where F is in I and F is not 0. Then S is not empty. It's not empty because F adjoin X has non-zero elements in it and is a subset of actually n including 0. It could have been that we picked an ideal that has a constant term, a constant polynomial in it, in which case that will have degree 0. So we have to use n0 here, so n including 0. But that's fine. It's a subset of n0 and it's a non-empty subset. So S has a least element. In particular, since S has a least element, there is an element of degree smaller than or equal to any of the other degrees in I. So that is, there exists some F in I such that the degree of F is less than or equal to the degree of G for all other elements of I. Okay, so we found our smallest. Now we have to argue that this smallest guy, the ideal it generates, is all of I. So we now show that the ideal generated by I is f of x. The containment this way is clear. So as a consequence of just f of x is an element of I, and so all the multiples are also in I because I is an ideal. So we only need to show the other containment. All right, so let's take some g of x in I. Then by the division algorithm, there is q of x and r of x in f adjoint x, such that when we divide g by f, we have the quotient q and we have the remainder r, where there's a condition on r, the degree of r is strictly less than the degree of f. Okay, but as in the proof for z being a PID, this allows us to write r as g of x minus f of x times q of x. Now, this guy is in I, multiple f's in I, so any multiple of f is in I, and I is closed under subtraction. So this whole thing is in I. Okay? But the degree of r is less than the degree of f. But and what do we know about f? F is the element of I, the non-zero element of minimal degree. Well, we have another element here, r, of degree less than it. How can that be? The only way that that can be is if r is actually 0, in which case the degree is negative infinity, right? Because to form our set S, we looked at the degrees of non-zero elements. So since f had minimal degree, it must be that r is 0. And if r is 0, g is a multiple of f. So it belongs in the ideal generated by f. And so that's the reverse containment. And so it must be that I is the ideal generated by f. Okay, so what do we show here? We had to find some way of coming up with the smallest element of I. Once we had that smallest element, that's our candidate for a principal generator. And so we then had to argue that the ideal generated by it is in fact all of I. One of the directions was simple, and the other direction uses the division algorithm. And so this seems to indicate that if you have a division algorithm, then you should have some notion of something being less than or bigger than the other. That's sort of part of the data of the division algorithm. And if you have that, it seems to indicate that you can run this proof again, and you can do it again and again whenever you have that situation happening. And so this leads us into this modified type of domain called a Euclidean domain, which we're not going to get to in this class, or at least not this semester. But we've mimicked the proof that Z is a PID almost exactly, and this sort of concept generalizes, is my point. Let me also notice something that we notice with Z. This is actually, the proof is actually an algorithm. Well, it's not necessarily an algorithm, but it's directions for finding a principal generator. What do? You look for a non-zero element of minimal degree. And if you can find that non-zero element of minimal degree, then that's the principal generator. So that's how you actually find them.